wonderful introduction. I hope that I'll live up to what you were telling about me. On a personal note, it was great to have you as a colleague for so many years. So I will be talking in Aspen. It's a wonderful setting, and I just love to breathe the atmosphere of a Center for Physics. We're talking about superconducting qubits. And again, I'm involved in a small part of the story. So most things that I learned is from my colleagues. And there are groups. It's Rob Shelfkov, Gerwin, Michel Debarret, and the younger people that I had a fortune to, and have a fortune to collaborate with, as well as other members of these three groups. Again, as I said, I'm not specialist in the, real specialist in the entire area. It's very broad. So I have a bit of impressionist painting in my head of the field. So please take this into account, that some things may be somewhat blurred. So with that, I'll tell about outline. So I'll tell what is the notion of a qubit, kind of standard story. And then substantial part will be kind of a very basic physics of superconductivity, but in small size superconductors. And the key point will be production of this qubit transmon that became really kind of a workhorse of many devices that actually now actively are used, or I would say explored/used. Then perhaps I'll tell in some detail about the decoherence, and other things will be just very cursory, like one screen per topic about a qubit, multi-junction qubits, coupling qubits, and example of logical gate, and the idea of the error correction codes. Very, very simple, which I'm able to understand myself, I hope. So with that, what is a qubit? Essentially, it's a controllable two-level system. And it should allow accurate state preparation, should have long coherence times of free evolution when we do nothing with it and just let it evolve. Then one must be able to accurately read out the state upon evolution, again, with the limitations that are set by quantum mechanics, but not by apparatus. And lastly, one should be able to do programmable connections to other bits, do the logical operations, what is called logical gates. Now, a simple example is just spin 1/2. So in magnetic field, the levels are split, right, by Zeeman. And we can create a state by applying some pulse. And if you pick the correct shape of the pulse, then you can field the spin. The wave function will be encoded. It will be a linear combination of spin up and spin down with the coefficients that depend on two angles, theta and phi. People like to plot it as a vector unit sphere, which is called Bloch sphere in this kind of science. So just a point on the Bloch sphere. Then, if you want to connect them, basically it's introducing some kind of exchange interaction between the spins with exchange tensor that is time dependent and in your hands. You can turn it off, turn it on, make it anisotropic. So that's what the programmable exchange means. Now, if you tilt the spin and let it evolve on its own, then it will precess, right? And that's the wave function, how it evolves in time. And this is wonderful, but it's ideal. And in reality, system tends to go back to equilibrium. So this direction of the field, basically the state 0 is a ground state. And if I just flip the spin, and it will look downwards, over time it just will find its way to go back, okay? And the average value of sigma z will go from -1 to 1. And this is a plot. It's not for spin, I just warn you, and I obscured here the times. It's just a schematic graph that one would see for a generic two-level system. Now, it's a hazard, right? But it's not the only hazard. So, another thing that happens is that You can see it if you just pull the spin to the equatorial plane, okay, and it just goes around. Great. Now, of course, because of the relaxation to the original state, to the North Pole, over time t1, the projection on xy plane will go smaller and smaller and smaller and smaller. That's why the sigma x will shrink, right? But it's not the only one thing. The other thing is that, as it happens, this omega naught, the frequency that I assumed fixed, in reality it's not fixed. It's fluctuating a bit because of various reasons. And if just for Gaussian fluctuations of omega around some average value, omega bar, there is additional decay, kind of scrambling of the phase, because the spin picks up a random phase, which is increasing with time, and that's this decay which is called the dephasing. This is the effect that was called dephasing, and there is characteristic time tau phi. So again, that's just an illustration. It's not for spin, but just to show how things kind of look in practice for generic level system. So these are the problems that one has to kind of fight with to get a qubit. Now, challenges, again, at my very superficial level, there are challenges that are specific for single spin. The first one is small exercise, and I'm not sure I get the numbers right, but I think it's more or less right. So MRI, magnetic resonance imaging, which is basically NMR, right? Nuclear magnetic resonance. It has some resolutions that is basically set by what FDA allows for the gradients of magnetic field applied, for the magnetic field applied to the human body, which constrains the gradients of magnetic field. Well, to make story short, basically the typical resolution, as far as I understand, is about 1 millimeter. Right, and the number of nuclear spins there is like 10 to 21. It's huge. So basically, you don't need to read out one spin. Okay, so what MRI machine does, it picks up a signal from huge number of spins. Quantum computing, you need, either all these guys are moving together and form like, 1 degree of freedom, or you pick up just one spin, right? Microscopic quantity. So if you're talking about spins in a solid, and especially electron spins in a solid, then it's kind of very difficult game because of lots of other degrees of freedom. It's hard to isolate electron spin from all these other degrees of freedom. There are lots of various kinds of interaction that couples this spin to other degrees of freedom, charge, and basically phonon, like oscillations of lattice. So it's a difficult game. Now, again, things change a bit for nuclear spins, and especially if we get rid of the solid state environment. And then there is kind of inherent tension between non-coherence times, which require kind of good isolation from the outside world, and fast readout, which actually requires to probe the spin, so to connect it to the outside world. So it's a generic thing, and it's not. I think it's not specific for spins. Now, so who are the contenders to implement good qubit? So once again, perhaps this is controversial, but this morning actually in one of the talks was called ions were mentioned, and indeed there is this direction. Problem is that ions interact on a long distance with each other. So I don't know. Another thing that apparently is rapidly developing are the Rydberg atoms, and it's new. I don't know much about it except rumors, so I will not talk about this. And then there are these superconducting qubits, which actually are studied for, I don't know, 15 years more, and give some some path to move forward. Now there are two kinds of qubits, I would say, within superconductivity area, and there are exciting things, and the example would be Marana thing. So once again, I mean, okay, it's a picture, and you can make jokes about it. I mean, I'm pretty serious that I just raised my head to Microsoft, who spends lots of resources on, or at least on our scientific level, resources to perfect this thing, which is based on very deep concepts of topology and physics used together. But for implementation, it requires basically conceptually new kind of materials. and it's extremely hard. And hopefully it will eventually play out. But I would say that, people like to use the word moonshot. Again, I'm not the native speaker. I would say it's kind of an Andromeda nebula shot. It's pretty far, and it's a noble thing. Now, another kind of more down to earth, which I would call working, you just can pick from web site, the commercial pictures of the devices. It's Google and IBM. It's typically 100 qubits, more or less. And these devices do work. In which sense they work? They do allow us to solve maybe impractical and kind of made up problems, but pretty complicated computational problems. So in this respect, these things do work. They're reproducible, and there are not more than just two big companies that do it and do it successfully, in the sense that by recipes they do something and it does what it's supposed to do. So these qubits, these machines are based on qubits. They're made of small pieces of a conventional superconductor. Typically it's aluminum. And that brings me to question, is what is superconductivity in a finite size, okay, especially small size. Now, common law is superconductivity breaks U1 symmetry. And the order parameter of a superconductor is a complex scalar with a well-defined phase. Now, that's great, but this U1 symmetry breaking means that the charge is not conserved. But it's great for theory, but if you take a piece of aluminum foil and put it on dental floss and ask your friend, an experimentalist, put it in a dilution fridge, I don't know if he agrees, but it will go superconducting with all the attributes. So, a piece of neutral material becomes superconducting with Meissner effect, and this is just from Scientific American or something, and it's a piece of high TC material that just levitates when it's going through the transition temperature. So clearly in this piece, the number of electrons is well defined and they have no way to leave, right? So there cannot be violation of charge conservation in this respect. So how does it work? We start from Hamiltonian. Okay, and of course, and it's non-relativistic physics, so Hamiltonians are good. You don't need to go to Grandgens and actions, just Hamiltonian is good enough. And it's a particle number conserving operator. So there are equal number of annihilation and creation operators of fermions, okay? And the instability is achieved when this term corresponds to, say, short range attraction. Attraction is important. Short range is very useful for theory. So this minus sign stands for attraction, V naught is positive. So then the usual way to proceed is to say that, okay, let's do what is called Bardeen-Cooper-Schrieffer BCS mean field decoupling. So we replace pair of operators by the average, okay, forming the order parameter, complex number with well-defined phase. And then we replace these four fermion interactions that is hard to treat by a bilinear combination, okay, which is easier to treat. Okay, so here we just went from the true Hamiltonian to the mean field Hamiltonian with prescribed by us value of delta, which will find then self-consistently, but for now it's just prescribed. Now, this thing, it definitely breaks charge conservation because we have just two creation operators or two annihilation operators. It preserves parity, but not the number. Parity of number parity, but not the number. And then let's just do a short detour. So to make it short, I'll just replace this p squared over 2m minus ef by xi. Okay, and this Hamiltonian is bilinear, so you can diagonalize it and find everything about it. And in particular, you can find the ground state wave function. Now, it's not exactly that. It's a textbook thing, but not exactly in all textbooks. So instead of doing the usual Bogoliubov rotation, which at least condensed matter people I think all know and love, I can write here the full anybody ground state wave function. So 0 here is just for number of particles. No particles there, and then we fill up particles in some special way with this product of operators acting on separate orbitals. Now, the excitations are some linear combination of psi and psi dagger applied to the ground state. and excitations form continuum. It's important that continuum is separated from the ground state by a finite gap. We're talking about conventional superconductors, S-wave, no zeros, no nodes in the separating or in the gap. So it's a finite gap, ground state, then gap, and then continuum. Let's look more on the ground state. So this is U is just a C number. This creates a pair. So each orbital is filled by a combination of a vacuum state and two particle state. So the particle concentration is literally broken at every orbital state. Well, in all truth, this U and V are behaving as shown on this graph. So, for example, if delta is 0, which is normal metal, then V is 1 up to Fermi level and then 0. U does other way. So there is no overlay between the U and V. So this function will conserve the number of particles, and the particle number will be exactly equal to what is the normal state. But you include delta, and then there is some sliver of states around Fermi energy where there is combination of vacuum and two particle state, and particle number is not conserved. So this is a nice ground state. You can calculate the ground state energy, and it's an eigenstate of this Hamiltonian. Okay? But because of this linear combination, it is not an eigenstate of electron number. So this thing is definitely not an eigenstate of this operator, which is just the total number of electrons. So what we can do is to look a bit broader on this ground state as a variational ansatz, the original Hamiltonian, which does preserve the number of particles. Okay, this guy is good. Now, this function as a variational ansatz is amazingly good. And it becomes, I would say, symptotically exact for large size and small gap system. Okay, so corrections, it's a bit of an issue to calculate, but basically they decay visually fast with the volume. So basically, we find a variational ansatz. Okay, the energy is independent of phase. And it's not just one ansatz. It's a family of ansatzes because I can vary phase from 0 to 2 pi. So it's a degenerate manifold of states. And we can use the fact that it's a degenerate manifold by making a linear combination of them. Okay? So you see what happens here is that to get a non-zero value of this integral, you have to compensate this e to minus I and phi as a proper number of e to I phi's from this parenthesis. Okay? You have to pick up exactly n pairs to kill this n in front. Only this term will contribute to the state. So therefore, this state will be an eigenstate with a number of particles. To be more precise, it allows to build any even eigenstate of the electron number operator. So that's how you can make a wave function of a finite piece of superconductor without basically losing losing a phase, but not the physics. So now we have basically two representations. We have phase representation and charge representation. There is a relation between the two. And this is eigenfunction of a number of pairs. And here's a small dictionary. So one more thing. So, this psi of phi is periodic in phi, right? Because if you go from 0 to 2 pi, you'll get the same function. So psi of phi satisfies this periodic boundary condition. And then, having these two bases, we can have a small dictionary. So operator n, which is diagonal in this representation, becomes operator minus IDD phi in phi representation. It's a one-line check by doing things by parts. Now, there is another important operator that raises the number of pairs. So it takes state n and creates state n plus 1, okay, for any n. And this, again, it's a one-line, basically one-liner with some iteration by parts. You can show that this operator, the raising operator, which is off-diagonal in n representation, is operator of multiplication by e to minus I phi. And in general, if I look at n and phi as operators, then in the ground state manifold, okay, so I'm talking about states that basically are degenerate within the ground state manifold. Right? So there is this commutation relation that basically it's a angular moment commutation relation for a rotor. So So these two representations, we'll use them intermittently for a while, but actually the phase representation may be more convenient because it kind of allows to use machinery of BCS theory. Now, so far, we had just short-range attraction, okay, and no real Coulomb interaction. Electrons are charged, right? So the leading, because Coulomb is long range, the leading effect of Coulomb interaction for a finite size piece. It's what we learned in high school electrostatics. There is charging energy, okay? So if you take a metallic ball and put some extra charge in it, it will get some energy. Q squared over 2c, right? So that's your Q squared over 2c. And again, at this level, capacitance scales linearly with the size. And E is the number operator for electrons. And we can project again on the low energy, on ground state manifold. Then this n hat becomes 2n as number of pairs, and that becomes minus IDD5. Right? So that's what sits here. Now, just for reference, the energies that I'm talking about, there is a big difference. So delta in aluminum is about 0.36 MeV, is small m. And so my experimental colleagues, that, you know, it's like you catch a spy. If you use MeV, he is not native for it, or she native to the gang. Gigahertz. So h bar omega equals E, and this is in gigahertz. What is this in millivolts? So EC charging energy is way smaller. It's everything is well below the gap. Now, another element that we need is the coupling of two small superconductors, boson junction. So again, if it's a weak junction, then it allows basically passing electrons in pairs one by one. A pair goes and then another pair goes. Getting two pairs tunnel to tunnel in a single quantum act is hard if the barrier is high. Now I'm talking about tunneling of pairs rather than single electrons because of the gap. And I'm interested in low energies where we transfer electrons from condensate in one side, condensate into another side. Okay. So 2e. And this operator can be, this condition can be written as an operator where I raise the number of pairs to the right and reduce the number of pairs by one to the left. Again, this T dagger is n plus 1, n, right? So that, again, in this low energy space, it's just e to minus I phi, and that's your Johnson interaction. So basically, the Hamiltonian that makes it possible to tunnel back and forth the condensate pairs between the two sides is a J cosine right minus phi left. And that's the resulting Hamiltonian. So the Hamiltonian consists of two parts. This EJ over cos phi, that's, you know, this is most standard textbook about superconductivity and Johnson effect. And this part, if you wish, it's even more basic. It's school level electrostatics. N is just charge, and n hat is a number of Cooper pairs transferred from one side to another through the junction. Now I sneaked in another quantity here, this displacement charge. And you can imagine that on top of this device, let's call it device, also put some electrostatically coupled gates, and you can bias it by some battery, which will create a polarization charge between the two, right? So this N is kind of polarization charge on the left side compared to the right side. And that, of course, will shift N hat by something, right? So it's like changing continuously the ion background by some external means. So here we go. Basically, this is the simplest, most elementary version of a superconducting qubit. You can introduce effective, typical energy, JEC, square root of JEC, that you basically can get by expanding cosine phi to the lowest order, to phi squared, and treat it as an oscillator, and then the oscillator frequency will be this square root. Required these excitations are well below gap. So we are still good talking about the ground state manifold. Yes, please.
Maybe it's a stupid question, but like in supercurrent, right? There is no noise of 2e, right? It's the supercurrent is noiseless.
Yes.
Can I think really on this, like what you describe of tunneling of 2e? Is it really tunneling or?
No, it's tunneling. It's definitely tunneling, but
there is no quanta of.
But there is no noise. I would say that you can. Right. I guess that if you want to be colloquial, I would say that because of the junction, you form a superfluid that kind of sloshes back and forth between the two. Okay, and there is no any backscattering. So, when you're saying that charge is discrete, you can know this only if there is backscattering. So, for ideal in your field, if you take just point contact with ideal conductance, it's also noiseless. Right? You need to have some backscattering. Right? My point would be that here, you simply don't have backscattering. You cannot scatter into some other state. It's just condensate to condensate. Okay, so it's a hybridization of two condensates. Each of them, say, it's just one state, and they hybridize in something. Okay, so does it make sense? Yeah, please interrupt because it's much better if there is some discussion. Right. So here is periodic boundary condition. So we can gauge out and out of here, right? So just doing some transformation. And then there'll be no charge here, but it will stick in the boundary conditions. So basically, if you wish, it's a rotor where I can twist boundary conditions by the external charge. Now, obviously, it has discrete spectrum, right, because it's on a circle. And you may say, no, that the larger EC is, the more non-equidistant spectrum is. So let's pick the two lowest levels, and that's our qubit, right? And if it's non-equidistant, then the next level is much higher, and we don't care about, so it's two levels. Well, the advantage of superconducting qubit, at least at the superficial level, is that a single degree of freedom here is carried by condensate of many electrons. So for typical size, it would be at least 10 to 9 electrons, actually more. Okay, and there is a gap that separates this degree of freedom, at least from the electronic degrees of freedom inside the device itself, inside the superconductor itself, because states above the gap, the particles are 0.33, 0.17, 0.18 MeV up. Now, that would be good, but this n is not as innocent as it may sound. So all the levels depend on it, right? So basically, you change the boundary conditions, and the levels move. And the thing is that this n is any charge foreign to the condensate. So of course, there is gate that I just put by hand there. Actually, you can do it. But then there is a background variational charge that varies in time. On a slow scale, it's not controllable. It's not clear where it comes from. It's some substrate from whatever. And then there are quasi-particles that tunneling of this one actually does produce noise. So quasi-particles tunnel from continuum to continuum. They can backscatter. They can do everything. The main thing is that when they tunnel through the junction, they change the charges by plus minus e. Okay, so this guy changes a number of pairs, say, by 1/2, discrete jumps, and therefore this frequency that I wanted to stay stable fluctuates. That's bad. So this is actually what was bad in the beginning of this journey. These devices, I think, usually were called like Cooper pair boxes, something like that. So how to fight this noise? How to fight this dephasing? Before doing that, I'll just give an illustration of the charge dispersion. So that's a separate experiment outside the story. But basically, if you do measurements fast enough so that this delta n doesn't have time to change, then you can see how this difference changes with the gate voltage, it's n bar. And because of the symmetries of the epsilons, which are periodic in n and also even in n, there are two special points in the gate voltage where there is no difference between, basically where this jumps plus minus E over 2, plus minus E, sorry, will not do anything. So in these 2 points, there are jumps, but they don't do anything. If you're away, then jumps will change the frequency. So that's a clear manifestation of this term. Again, it's very hard to control. So how to fight it? If you look at this Hamiltonian, condensed matter people, it's just basically one-dimensional particle moving in one-dimensional potential, periodic potential, with some quasi-momentum, right? So this n plays a role of quasi-momentum. So what one can do is just try to reduce the sensitivity to boundary conditions to make the band narrow. So basically, a particle tunnels through the cosine potential, okay, and that forms what I would call bandwidth in parentheses, because n is not a quasi-momentum; it's just external parameter. But you spend this this sliver of energies, this range of energies, by changing n from 0 to 1. This bandwidth is different for different levels. So the distance between the two levels is roughly this frequency that I introduced already. It's kind of a harmonic oscillator frequency. Now the width of the bands is exponential in EJ over C because it's probability of tunneling, right? So the higher the barriers, the harder it is to tunnel. Therefore, the narrower this strip. Okay. So you can get exponential suppression of frequency fluctuations by making this ratio EJ over C large. How large? So if you take this EJ over C over 200, it's large enough to make this effect not more severe than other effects. So basically, this would be sufficient. A remarkable thing that if you do that, then basically your Hamiltonian becomes a Hamiltonian of slightly harmonic oscillator. So I expanded cosine phi to first 3 terms, constant I just threw away, I squared in phi to the 4th. So this phi to the 4th is kind of small fraction, and it's amazing that at this level, the harmonicity coming from this term is sufficient to distinguish between the transitions between 0 and 1 and 1 and 2. So it still allows to address exactly 0 and 1 transition. It's 2 levels, form computational subspace, and by and large evade exciting or kind of ionizing the qubit higher energy states. So that's revelation in theory and an experiment basically was done in the paper of 2007, and that was kind of, I would say, ushered the way of quick developments of this technology, because these things are robust, they're reproducible, and very simple by nature. So that's was the achievement. Typical numbers, again, not from this particular paper, but typical numbers that to delta is aluminum, it's about 88 gigahertz. The frequency 0.1 is about 6 gigahertz, and the level of harmonicity, the difference between the two, is way smaller. It's only about 200 megahertz, but it's enough. It's enough to just to operate with 2 levels. So now I just
is reduced the capacitive energy.
Exactly, yeah. So what, the device looks kind of stupid because you have huge pads, tiny junction, and these huge pads, well, together actually with large capacitance of the junction, so the larger the capacitance, the smaller the energy is squared over to C, right? It's just that, yes, yeah. I'll show some micrograph of device in a second. So again, so this graph that I have shown before, but obscures the numbers, this is kind of, my understanding is more or less kind of run-of-the-mill bit. Transmon is from a review of 2019. And again, there are these vectors, T1 and T phi. So here for this graph, actually, T phi is something appreciable, as you see. But it doesn't come from charge. It's some more complicated device where it comes from some other sources. So charges here is not an issue. Yeah. No, absolutely. Yeah.
Symmetry reason why the phase variable should start off radically decaying Gaussian?
Yeah, this one, even this one. Oh, it's very simple. So if you assume Gaussian noise, then you'll get Gaussian. Or, yeah. Right, yeah. And it's a great simplification because if you go into details, there is 1 over F noise in all kinds of stuff, right? Which I have an impressionist picture. Yeah, exactly. Yeah. So, so now what about the energy relaxation, about T1 time? Again, this is a graph that I've shown obscuring the numbers. Again, run of the mill and give or take 100 microseconds. So there are lots of channels of losing energy for a qubit. And as Chandra noticed, so basically, qubit is the small junction and some pads. And it's a qubit, but it's also an antenna. So when qubit operates, it broadcasts. It just loses photons to the environment. And this parasitic radiation losses are in this simplistic view, is the worst thing. So one has to get rid of it. And on a simple level, the way to get rid of it is put the device in a cavity, detuned from the resonant frequency. So then a photon, in order to get to the cables, to outside world, to the continuum spectrum, it has to tunnel, goes virtually to the cavity mode, right? So it's a tunneling process called Purcell effect. And that isolates qubit quite well from the outside world. Again, this is kind of extreme, but it works. Then there are other sources, and there are lots of them. I will dwell a little bit only on one of them, quasi-particles, for two reasons. One is that I think that this one is reasonably well understood. Second reason is that I worked on it, so I cannot resist temptation to tell a few words about it. Well, there are more reasons. It's cute, but I have to admit that now it's not the. I guess that now it's not the limiting factor. That's kind of impedes the progress. What about this quasi-particle stuff? So as I said, the continuum spectrum is separated from the ground state by a gap. So the density of quasi-particles is supposed to be small, exponentially small at low temperatures. Now you can work out a theory and find that the relaxation time, energy relaxation time of a qubit, is proportional to the density of quasi-particles. I measure quasi-particles in dimensionless units, dividing their density, physical density, by the number of states in energy sliver fits to delta around the Fermi level. Okay, so that's, we'll call it number of Cooper pairs, right? So typically at low temperatures, this XQP is 10 to minus 52. It's tiny. In any reasonable volume, you will not see any quasi-particles. So, but then you can measure this quantity and see what is XQP in reality. Why is it related? Basically, when quasi-particle tunnels, it may tunnel inelastically, just depositing energy or picking up energy from a qubit. Okay. In this particular case, it picks up energy from the qubit because it went from state 1 to state 0. So it went out more energetic than it came in, the expense of the relaxing qubit to the ground state. Okay. So now, what it turns out that if you just look at the data, at temperature, say, above 100 millikelvin, it's indeed activational and it fits reasonably well the theory with thermal quasi-particles, but then there is saturation. And again, here is a somewhat cavalier statement that the saturation proves the presence of non-equilibrium quasi-particles at low temperatures. Now there are way more detailed experiments. I will not talk about them. They do show that there is some saturation at low temperatures at the level of 10 to minus 5, 10 to minus 8, to minus 9 actually. And it's tiny, but it's steady. There are some improvements over time with better design and better shielding and everything. So it's not clear actually where this resident quasi-particles precisely come from. It's not universal, getting better. Now another thing that actually was mentioned also at Yale is that there are kind of quiet and turbulent times in the life of qubit. Sometimes it stays just in state 0, unexcited. Sometimes without any apparent external excitation, it goes to state 1, state 0, and does something crazy. So these are the parts. This comes sporadically. And it was a conjecture, actually, that basically the qubit does what we don't want it to do, namely to be a detector of cosmic rays. Because cosmic rays deposit about, say, 0.5 MeV is capital M. And if you just look how many quasiparticles it may create a lot. And then you just wait until you know they're going away, and that's what makes these noisy periods long. So again, it's a conjecture that it's cosmic rays. There are lots of experiments, actually. Well, not lots, but quite a few experiments that are trying to prove or disprove it, just for fun. So these people with this big device, 100 qubits, they can see these events because some qubits stopped working. Okay, and this is before the event. This is the beginning of the event, and then the error spreads, but gets weaker, and it spreads even more. It gets weaker. So this whole scale is about 10 milliseconds. Remember that coherence time, I said it's 0.1 milliseconds, so it's 100 times more. So, so that's basically a hazard. There are apparent ways to deal with it. If you make superconductor on two sides of having different gap widths, and it's possible to do this even with aluminum, just varying the thickness of aluminum for some technological or material science reason, you can hope for the following things: that the originally hot quasiparticles will relax to low energies, and if this energy becomes smaller than the gap difference, then they have hard time tunneling, because basically there will be no receiving state. There will be quasiparticle which will be there ready to tunnel, but there is no state to tunnel. So actually that works, and this one of these very latest papers actually does show how it works. It doesn't eliminate bursts, but it makes them much shorter, incredibly shorter. Now I have about 10 minutes left, I guess. So let me kind of go quickly about other parts of story. So again, with the dephasing and energy relaxation, I gave just two contributions. Actually, the big elephant in the closet, or it's not even in the closet, is the losses in the electric. And the electric actually is lossy for not known reasons. I mean, it's most probably it's from two-level systems that are hard to control, and which change in time, and they may be in the bulk or in the surface. It's a pretty active area of material science research, and there is a very strong group at Princeton, Natalie De Leon, who actually does quite important, interesting work on it. But it's I mean, for me, it's almost like alchemy, and I'm not ready to talk about it at all. So I will stop talking about dephasing stuff and improving the bit quality, and dwell a little bit on how you read out the state. Okay, so the idea is that you send a microwave which is off resonant. So the frequency of microwave, say, is 0.3 h bar omega away from the transition of the qubit, right? It's off resonance. And ideally you send, a weak signal, a weak tone, and it scatters, it reflects elastically. So you don't change the qubit state. You just look at the reflected microwave and measure the phase of reflection. It's what is called dispersive readout. So you try not to change the state of qubit, but pick information in which state the qubit is, 0 or 1. So clearly, almost clearly, the phase will depend on how close you are to resonance. And the distance to the resonance is different for state 0, okay? And state 1, there is a distance to state 2, so it's different resonant frequency. So therefore, the detuning of the frequency will be different. And that actually gives you a contrast, because the phases for state 0 and 1, phases will be different. So this is in a nutshell what is done. And of course, you lose signals. There are some amplifiers, and they are quantum limited and so on. But this is a nutshell what you try to do. You try to pick up the phase of elastically reflected photon. Now, this thing is that you want to do it fast. So basically, you set not one photon, but lots of photons. And then there is hazard because there are nonlinear effects. And there is no resonance with single transition, but n photons may resonate with some nth level of the qubit excitation. And that will be a problem because you'll just lose system from its computational space. So again, there are ways to fight it, and it's ongoing work, including like preprints of last couple of months. But again, the idea is that you try to pick the phase, and here is an illustration. It's data from Chalmers in Sweden, and basically these blobs are kind of multi-shot, single-shot measurements, many of them, and you see that they're concentrated in three different phases. And this 0 and 1 are good. It's just computational space, but there is also leakage from computational space, and there's some occupation of state too. That's what you don't like, but it's happening. So this method is actually quite well developed, and again, the fight now is to make it more reliable and less intrusive, so it has lesser chance to perturb the qubit state. So there are lots of various kinds of devices that are based on the transmon idea. So I was late to the party, so these devices are with split transmon. Good because they allow to change the frequency of the qubit, and that may be useful at the expense of having another element that threads the flux through some kind of a loop. Now, this one, the fluxonium thing, it's actually a different principle because the fight with the charge fluctuations here happens not because you just make EJ over EC huge. The fight is by inductive shunting a small junction. Basically, you can make a shunt that will not do anything bad at gigahertz frequency, but does everything that you need at much lower frequency. So it shunts the kind of static charges, almost quasi-static charges. That allows actually to get qubits which are extremely nonlinear. So basically, these are as close to level system as it gets. Now, why I'm talking about this kind of devices? Because they actually allow to couple qubits. And you can kind of inductively couple two qubits through a controllable coupler, which is tuned by mesomagnetic field and can turn on and turn off the interaction, which again varies kind of glossing over this. In some way, can materialize a sigma-sigma interaction between the qubits. So that's about the readout and coupling.
Sorry,
Yep.
So sigma polymetric to the 1 and -1 correspond to the 2 lowest.
Yes, yeah, absolutely. Yep. Thank you. I had to say it here. So this is sigma equals -1, and this is 1. Yes, thanks. Actually, that's important. I completely swallow. Yeah. Basically, as long as you're not losing computational space, you can encode it into spins. And well, I asked it. So again, there is a sigma z, sigma x, sigma x, which are physically very different for the circuit. It's like linear inductance or something nonlinear for sigma z, sigma z.
There's no natural like U1 symmetry.
There is no. There is no natural. I mean, it's all supernatural. You do whatever you want to pick up the right elements. Well, at this level, it's engineering. My understanding is that this kind of how the devices, commercial devices, work actually through like some kind of couplers. And in labs, so that's what I know, is that it's also couplers, but the most interesting experiments are where they're working literally in nonlinear regime and allow kind of to mix photons from the two qubits. Okay, so now I just want to, I loaded myself with recently, so let me share. So it's an example of two qubit logical gate, controlled NOT gate. So it's qubit 1, qubit 2, okay, and it's evolution in time, right? So now the input state, this ket vector, the first position here is the state of qubit 1. Second position is state of qubit 2. Okay? And this is the incoming state. Then we do some transformation. It's unitary, non-unitary. We don't discuss that. Transformation, a gate that is the output state. Now, for this controlled NOT gate, it does the following. So if you look at state of the qubit 1, you can check 0, 0, 0, 0, 1, 1, 1, 1. Nothing happens. So it doesn't change the state of qubit 1. What about state of qubit 2? So if qubit 1 is state 0, then 0, 0, 1, 1. Nothing happens. But if qubit 1 in state 1, then 0 flips to 1 and 1 to 0. So basically, qubit 2 flips only if qubit 1 is in state 1. Okay. So I'll give an example why it's useful. And that will be perhaps the last thing that I'll talk. So there is so-called parity check, and it's good to have it for some kind of error correction routine. Now, I don't know what error correction is, but what I know is that if I, over the phone, I'm trying to say my name to a customer representative, not AI, but real, and your first letter G, like in George, right? So G is just like 1 bit. And I attach 5 bits, George, 5 more letters, to make sure, or at least to have a lesser chance that G will be confused with something else. Okay? So basically, I produce huge redundancy in a hope to reduce the probability of an error. Okay, so now imagine that you have a qubit, and some agent encodes it in state 0 or 1. I don't know what is the state. The only thing I want is that this state is staying put some time t. And nothing is perfect, and there is flip probability of this qubit, and there is probability p, a small probability, 0.3, that it will flip. So at time t, I have a chance that if I measure it, I'll find a state, and I will never know whether it's initial state, and the probability that I made a mistake is 30%. So what one can do is to redundancy, right? So we have 2 qubits, and third one, which I'll call ancilla. And at the entrance, prepare states qubit 1 and qubit 2, both qubits, 0 or 1. You don't know which state, but the only thing that you know is that they are prepared in identical states, 0 or 1. Then you do this controlled NOT gate twice with 1 qubit and then with another one. So it's quite easy to see that the state of the ancilla will flip only if one of the qubits will flip, right? So they are both in state 1, okay? And then when it passes through 1 qubit, this guy may flip, but then it will flip again because of this one, okay? Only if they have different values, then you'll get -1. So do I know for sure that I didn't lose information? No, I don't, because if they both flip over that time, tough luck. It's still, they're both in the same state. I will not find it. But I cut the probability of an error from p to p squared. So it's from 0.3 to 0.1, 0.01. 0.1, sorry. So that's basically the idea of the simplest error correction code. Now, it's a classical thing, because here I don't think of linear combinations of 0, 1 with complex coefficients. It's just 0 or 1. And when you put complex numbers into the thing, it becomes way more complicated. And then next level complications that nobody is perfect, including the ancillas. So separations are also not ideal. Then even the question about whether it's in principle possible to get a correctable routine, taking into account both errors in the qubits and ancillas. It's a very interesting question that in some cases may be mapped onto some kind of very intricate statistical physics. But that's well beyond expertise and I guess beyond this talk. So I guess what I would like to finish with is I would not say outlook, but challenges. And again, as I said, I have some kind of impressionist view of this field, so it challenges as I see them, not necessarily right peak of problems. So one thing I'm pretty sure about is that extending the qubit coherence time is important. So it's physics / material science / engineering, and it's a real thing. So the longer the qubit coherence time is, the better. Another thing that one has to improve the fidelity of the logical gates, which includes, this readout problem, improving readouts, improving the state preparation. So that's another important frontier. And then implementing the robust quantum error correction protocols, which hopefully will enable people to create a correctable logical bit that can be corrected, no matter what. And there are different estimates on how many bits you need physical bits to create a logical bit that will be correctable. It's a separate story, and I think that it's a very interesting and intriguing direction that kind of spans both physics and computer science. Stop with that, thanks.
Thank you very much indeed. We have a little time for questions, so please fire away.
Yeah, thank you for very interesting talk. So my question is concerning the possible effect of cosmic rays. Does it help to do the experiment deep underground or something?
Yes, Grand Sasso. Yeah, thanks. It's not prepared question. Yeah, so there is a group in Karlsruhe, Jan Pop. They made some arrangements and took their device down to Grand Sasso. So my understanding is that it did reduces the probability of errors by 30%. Okay, and again, cosmic rays perhaps are there, but maybe there are also some other factors. Another thing that one can do is to change the orientation, because I think that these kind of experiments are also, I'm not sure, but I think they were performed, and there is some difference between the two.
So, yeah, you mentioned that the Google and IBM both use superconducting qubits.
Yes.
Is there any difference in architecture, or?
I don't know. I think that first of all, I think that for various reasons, they not necessarily call them transmons. They call them demons, xmons, and so on. But it's the same device. So now about architecture, I mean, there was a combination of secrecy plus my ignorance. So I think that they all use well, basically it's a 2D array, right? And you couple the qubits through additional qubits that are flux controllable. The problem, I think, one of the problems that I just know from literature is that you have to constantly tune the qubits in order to have their frequency to avoid the two-level systems and all these problems in dielectrics that exist.
For the same kind of quality of qubits, supposing you increase the number of qubits from 10 to 20 to 30, etc., does your flux noise remain constant, go linearly with n, go quadratically with n?
Flux noise?
With n?
You're talking about?
Ultimately, you're being limited by some kind of flux noise in your
No, frankly, I don't.
times. The characteristic times in which the circuit remains. Okay, the coherence time.
Yeah.
How fast does it go down with increase in n? Where n is the number of qubits?
I frankly don't know. Maybe it's known for particular devices. I don't think there was kind of a generic treatment, and I think you're saying flux noise, but there are lots of other. There's crosstalk between the qubits.
Coherence time, which takes care of everything. How does?
Yeah. Coherence time I can define for a single qubit, but I'm not sure how to define it for a qubit in a device. That's different. You think that, okay, you can go flying.
Yeah, so I have a question. It's a two-part. First, why aluminum? And second, if I ignore like ease of fabrication and cost, is there like a dream superconductor with dreamy properties that would somehow help with some of these challenges?
course, there is a dream, but it's a dream, right? So if you have a superconductor with gap order of room temperature or higher.
Yeah, sure.
Yeah, so, yeah, but thanks for the question. So the thing is that aluminum, again, what I'm going to use by osmosis, so it's not. People know very well how to do junctions. And draw some junctions with aluminum, although they look awful on a micrograph, work fantastically well. And even when people try to do, so one of the ways, to go to higher gaps is to use some higher TC material, like niobium nitrate, for example. Still, my understanding is that what one does is proximitize aluminum. So the junction is still aluminum. Okay.
Because aluminum oxide makes bonds very well, and it's a good instrument.
Yes, yeah, right. So that's, I guess that's a short explanation, yeah. There is a dream, but hard to, yeah.
So maybe I just got confused, but it seemed like the biggest problem was the out of equilibrium quasi-particles. So, I mean, it seems like would increasing the gap help?
Yeah, okay. So first of all, it's the biggest problem what I described. So, and I have to humbly admit that except the bursts, the particles are not the biggest problem. Okay, they are biggest problem over short times after the burst. Now, bursts, again, if it's cosmic rays, perhaps it's very hard to get rid of it because basically they go through, right? Now, for this case, what are the mitigation things? So, actually, you are right to some extent that increasing gap by another millivolt will not do much. So in this case, basically, what you want to do, well, one of the approaches is to essentially to trap quasi-particles to not allow them to tunnel through the junction. So here is a very cute element of elementary physics. So the qubit operates at microwave, at gigahertz. From the point of a piece of metal, it's almost a static field. So all the voltage of the photon h bar omega of 10 gigahertz, also the junction, okay? So if quasi-particle is somewhere in the bulk and doesn't cross the junction, let's leave it there, nobody cares about it. It should not cross the junction. If you somehow trap the quasi-particles away from the junction, it will help. But how you do it? You have to somehow profile the leads so that they have some traps, put a normal metal, but it has other problems than associated with that.
Questions? I have just one. So you have a ground state and you have a first excited state, and they give you your spin up and spin down. And of course, there are other states. Up to now, it felt like you were saying that if you excite into the other state, you just get it. But is there any sort of engineering or state control where you can kind of figure out what's in this extra state and bring it back into the fold?
Yeah, so again, I simplified, and the level I understand actually is that the higher states can be actively used. And as a matter of fact, you can kind of store a state in out of computational space and then put it back. So these things are existing, and at least at the research level, they are used. So yes, you can make use of higher energy states, but also they may also do some harm.
Sure. Thank you. Any further questions?
Can I ask one more?
Yeah.
I think I kind of missed something. You showed a bunch of different designs of qubits, and you said in some of them you don't need to make these big pads to increase the capacitance.
Yeah.
So it seems like in some of them you're adding more and more junctions. Is that
right? Yes. So you know what? Maybe you give me a reason to show a slide that I think I didn't plan to show. So this is the first implementation of this fluxonium qubit, and this is a real thing. So these are these 43 junctions, and They are fairly big, so it's basically classical it's classical junctions. And this whole thing can be viewed as an inductance. So inductance is different from a junction because there is no periodicity in phase anymore. Basically, you dial a phase, say 2 pi at the ends, you never have a phase slip in the junction. It's like just a classical, it's just an inductor. And with this inductor, you shunt a small junction. The small junction actually is this active element, is your qubit. But it's shunted by the inductor that for DC or for low frequency noise, it just shunts the charge because it's well allowing charge to propagate, say, at the frequency of 100 megahertz. But at gigahertz, it's like an insulator. So that's another way. Now, actually, that was done with junction, and I couldn't believe that it will work. And as a matter of fact, it started with Michel. We thought about doing something very cute in solid state, in condensed matter physics about Kosterlitz-Tauris transition 1+1. And it turned out that it had a chance to work. But the leftover was this engineering thing that actually was a new design. As you see, that EJRC for the active junction is small, so it would be extremely noisy in terms of charge. But because of the shunt, there's basically no charge noise. What people do now is they try to develop so-called inductively charged inductively shunted qubits, not with junctions, but with some material that has very large inductance just by nature. It's also strongly disordered, some semiconductors, so thin wires.
There are no further questions. Let's thank our speaker one more time.